a little late. So what this gives us is that another omega, d theta by dt is another omega. So we got r omega squared. And then you have a negative of cosine theta x, negative of sine theta j. This is a minus r. So you have an acceleration that is r d omega by dt times et. It is tangential acceleration. And then minus omega square r. This is centripetal acceleration because it points toward the center. Or we prefer to use it centrifugal. Okay. Actually, this is centrifugal means away from the center, but centripetal means point toward the center. So this is supposed to be centripetal acceleration. I'm not used to this. Centripetal acceleration. So you have now, in this case, two acceleration, one tangential to the motion and one point toward the center. And suppose that your omega is uniform, omega is constant, it is a uniform circular motion. This term will go to zero. You only have the centripetal acceleration. So there are two acceleration here. Let's see. Suppose particle is at this point, and then suppose this is x-axis, this is y-axis. This is vector r. And then this is vector v, or velocity. And then you have two acceleration. You have at point that way, and this is ac, point toward the center. So you have two acceleration here. And the at, or tangential acceleration, is r times d omega by dt along the et. And alpha, or d omega by dt, is called angular acceleration. This is tangential acceleration is alpha r. Okay. So theta represent angular displacement. Omega represent the angular velocity or angular speed. It should be angular speed. Sometimes they call it velocity, but it is have a sense of scalar, not the vectors. Now this is angular acceleration for at, and you still have ac. We still have AC, which is centripetal acceleration is minus omega square r. Okay. Point toward the center. Okay. Or you can say that it is minus omega square r, and the unit vectors of R. Or you can say that this is minus V squared over R. And the unit vectors of R, meters per second squared. And this is centripetal acceleration. So to sum up, we have a angular motion or a rotation. We have theta represent angular displacement or angular distance. We have omega represent the angular velocity in radian per sec. And alpha is represent the angular acceleration in radian per sec square. All three of this is scalar because the vectors is already taken care of. We talk about it as a scalar function. Now let's take a look at some example. Okay, for an object that moves with constant angular acceleration, supposed to have this term angular represent here. Here you should have angular acceleration. If alpha is constant, we know that the tangential acceleration is constant because R is also constant. We have alpha is d omega by dt, or d omega is alpha dt. Now making an integration of this, integration of the omega from omega 0 to omega equal to alpha dt from 0 to t, you get the relation of omega minus omega 0 equal to alpha t, or which is, it is parallel to in uniform acceleration that v equal to u plus at. So these two equations like an equivalent. This is linear motion, and this is angular motion. Now, if you do another integration of omega, by definition, omega is d theta by dt. This is by definition. So it means that this term have three lines. By definition, d omega by dt is omega angular speed. So this is d theta by dt equal to omega 0 plus alpha t. So d theta is omega dt, or d theta from 0 to theta is 0 to t of omega 0 plus alpha t dt. And this integral gives you theta equal to omega 03 plus alpha t squared with 2. This is equivalent to x equal to ut plus 1/2 at squared. And if you plug in that t equal to omega minus omega 0 over alpha, okay, So if you use here T equal to omega minus omega 0 divided by alpha, and plug into T's, both of them, and then you rearrange the term. What you will get is omega squared minus omega 0 squared equal to 2 alpha theta. Well, actually, I showed it on the right side. By doing this, theta is omega 0 t over 2 plus omega 0 t over 2 plus alpha t squared over 2. And we have omega 0 t over 2 plus omega 0 plus alpha t times t over 2. And this is omega. So theta is omega 0 plus omega over 2 times t, and you end up with this equation. So we also have three equations, the same as constant acceleration, but this is constant angular acceleration. And let's put some summary page here. Just a moment, let me insert now if you compare between linear and angular, so this is linear motion. We have v equal to u plus at, and s equal to ut plus 1/2 at squared, and s equal to v plus u over 2 times t. And we also have v squared over equal to u squared plus 2as. And this is a is constant. And this is angular motion. You have omega equal to omega 0 plus alpha t. Theta, an angular displacement, is omega 0 t plus 1/2 alpha t squared. And then you have theta equal to omega plus omega 0 divided by the 2 and t. Then we have okay. we have omega square equal to omega 0 squared plus 2 alpha theta. And this is the same case, but where alpha is constant. This is a comparison to linear motion from the angular motion. Okay. Now, let's take a look at the example. Which is the Earth rotation. Now, our Earth, let's say our Earth is rotate around the axis, which is the north-south axis. Well, it's called rotational axis. It's not a magnetic field axis. However, when you looking for north, we use the magnetic field, the magnet, to point out the direction north, and that is a magnetic north of the Earth. And luckily, they are coincide. They are almost at the same place as the rotation axis of the Earth. So the Earth is rotated around this axis 24 hours a day. One revolution actually is not exactly 24 hours. The Earth is rotated around this axis one round in 23 hours, 56 minutes, and 4 seconds. And within that, we just say approximately 24. Find the angular speed of the Earth rotation about its axis. And the question is, how does this rotation affect the shape of the Earth? Now, this is quite a discussion because we have the relation that V equal to omega r, or is 2 pi r over t. The angular speed of the Earth is V over r, or 2 pi over t. So the angular velocity of the Earth is one complete 2 pi radians in 24 hours, or the period of rotation of the Earth is 24 hours times 60 times 60 seconds. So for Earth rotation, we have omega equal to 2 pi over 24 times 60 times 60. It is 7.27 times 10 to the 5th radian per second. That's the angular speed of the Earth. Now, for us, we are at rest. Suppose what we are here now is that we are sitting on the, I'm sitting here on the chair, but I'm still at the surface of the Earth. So the velocity of any point on surface of the Earth at equator let's say it's equator is omega times r, and it is 7.27 times 10 to the 5th minus 5th times the radius of the Earth, which is 6.4 times 10 to the 6 meters. It's around 6,400 kilometers for the surface at the radius of the Earth. So let's do some calculation. 7.27 times 6.4 equal to 46. So it is 10 to the minus 5 times 10 to the plus 6 give you 10 to the plus 1. So this is 465 meters per second. So if you add the equator, let's say for Bangkok is not quite far from that. You multiply this with cosine theta. So 365 times cosine of 13 degrees. It is 353. For Bangkok, we are traveling at 453 meters per second at BKK or at Krung Thep. So right now I'm sitting here on the chair talking to you, but actually in space I'm traveling at 453 meters per second around this axis. So it is quite fast, but because the Earth is so big, we are not feeling anything. So this is the angular speed of the Earth rotation. And what does it happens to our Earth, to the shape of the Earth? Well, everything's that going around in circle will have a centripetal acceleration. But if we are at the surface, what we feel is that we feel the acceleration outward. It's called centrifugal. So the gravity, which is the force that the Earth attracts every body, every object, is G0 is Gm over R squared. Okay, G0, according to Newton's law, is G mass of the Earth over the radius of the Earth square. And it is 9.81 meters per second. Without considering the rotation of the Earth. Now, if we're considering the rotation of the Earth is moving around in circles, so part of this gravity is subtract off by centrifugal acceleration. Okay, so the gravity that we feel is actually G0 minus by omega R, omega square R cosine latitude. So at the equator, this centrifugal acceleration is maximum. So if we measure the gravity at the equator, we found that it is a little bit smaller than the value at the pole. At the equator, the gravity is approximately 9.77 meters per second. Well, you can find it by subtract off by omega square R. Using omega is 7.27 times 10 to the minus 5 that we working on a moment ago, and the radius of the Earth is 6.4 times 10 to the 6 meters. And you will end up having the gravities around the equator of 9.77 meters per second. However, if you are right at the axis of rotation of the Earth, which is the North Pole, and at the North Pole or the South Pole, the gravity there is without any effect of centrifugal acceleration. So the gravity at the pole is 9.81 meters per second. So this rotation affects the gravities on Earth. And as a result, when the Earth is forming, it's turned out that the radius of the Earth at equator is greater than the radius of the Earth at the pole. So the Earth actually doesn't have a shape of a sphere. It's actually a shape of an ellipsoid. The radius at the equator is a little bit bigger than the radius at the pole. And this is, we found out that in dwarf planet, there are one dwarf planet that have this problem. It rotates so fast that the radius at the equator is 1/3, is 30% bigger than the radius of the pole. So it is like flattening out of a sphere. So there's still another question. Right now, the Earth is rotated at approximately 24 hours a day and going around the sun in 365.25 days a year, or a day, 365.25 days per revolution. But in Devonian period, 400 million years ago, if you're interested in this, there are a documentary called from BBC. Okay, I just forget what it's called. Orbit. The name of the documentary is Orbit. They discuss about this. The 400 million years ago, they found in fossil of a coral. A coral is a marine animal. In Thai, we call pakarang. A fossil record from coral is recording the numbers of days in a year. So 400 million years ago, they found that 1 year at that time is not 365.25. It is actually 440 days a year. So that means that at that time, the Earth is spinning faster than it is today. Okay, so the question asks, what is the angular velocity of the Earth at that time? And assuming that the time in 1 year is constant, okay, and the reason for this slowing down is due to the gravitational tug from the moon. You know, the moon is pulling the water on the surface of the Earth and create a friction. So instead of so this small friction will cause the Earth to slow down. Okay. So at that time, you see the period of time in 1 year, assuming constant. So at this point, we have 365.25 days a year, and 1 day is 24 hours. So we have that at that time, the number of hours in a year is 24 times 365.25. But at that time, it rotates 440 times. So in Devonian 400 million years ago, one period of rotation of the Earth is only 19.92 hours, or approximately 20 hours. It is 4 hours shorter than today. And if we assuming that that is the initial angular velocity, omega 0, you got 2 pi over t, or 2 pi over 19.92 hours times 60 times 60 minutes and times 60 seconds. It turned out to be 8.76 times 10 to the minus 5 radian per second. We know that today the Earth is rotated at the angular velocity of 7.27 times 10 to the minus 5, and two incidents separate by 400 million years, or 400 times 10 to the 6 years. So we found that the alpha for the Earth is omega minus omega 0 divided by t. Okay. So that is the, I didn't work it out. So let's assume that you try to put these numbers on later. So what we have is omega today is 7.27 times 10 to minus 5. Radian per second. And omega 0 from this is 8.76 times 10 to the minus 5 radian per second. And t is 400 times 10 to the 6 years. So you have to convert it into seconds. So it's 4 times 10 to the 6, 78 times 365.25 to make a days, and then times 24 hours, and then times 60 times 60. Whatever it is, you can find alpha equal to omega minus omega 0 divided by t, in which I left for you to doing that calculation. Okay. Okay. Let's take a look at another example from survey 8th edition, chapter 10, page 308. During a certain time interval, the angular position of a swinging door, okay, is described by theta equal to 5 plus 10 t's. Okay, I would say it's in about 5 minutes. We're going to have the quiz. It's 5 plus 10t plus 2t squared, where theta is in radians and t is in seconds. Find the angular position, angular speed, and angular acceleration of the door at t equal to 0 and t equal to 3. Now, doing the same thing as what we done in uniform acceleration motion, theta is 5 plus 10t plus 2t squared. By definition, the angular velocity angular speed is d theta by dt. So take a derivative of 5, which is constant, give you a 0. Derivative of 10t, which is by dt, you get 10. Derivative of 2t squared, you got 4t. So you have omega is 10 plus 4t. And alpha is derivative of omega by dt. And it turned out that derivative of 10 is 0, and derivative of 4t gives you 4. So this is radian per second squared. Okay, so theta is at t equal to 0. What happened? At t equal to 0, the angular position is 5 radians, and angular speed is 10 radian per second, and angular velocity acceleration is 4 radian per second squared. Now at t equal to 3 seconds, you have theta is 5 plus 10 times 3 plus 2 times 9. It is 5 plus 30 plus 18, so it's at 53 radians. And the angular speed is 10 plus 4 times 3 is 22 radians per second. And alpha is 4 radians per second. So this is another example where I'm going to stop today and we will start the quiz. And let's see, we have one more example before we get to the Newton's law of motion and moment of inertia. Okay. Let me open the quiz. Here's the quiz. And the recording from February 9th, I will check it out and then put it on. So here's the quiz for today, and it contains 5 questions. So for 20 minutes, I think you have enough time to complete it.